Hello, community. Hey, it is so great that you're back. And yeah, I'm addressing here one person because I know that this video will only be watched and understood by one single person. And I do hope it will be you. So let's start here. And as you can see, we have some beautiful equation. And this is the system. We have here a mathematical equation, and then we have here an agent output here on a high level, where you can see that the agent says, hey, I understand mathematics, so those are here the step the system should perform. And then we do have here a low-level agent who is simply performing here the step-by-step mathematical calculation. And we call this an agent high and an agent low. And we were gonna build this system because we want to understand how to build this system. And yes, those are the equations that define the system, that define the dynamic of the system. But you know what? Those are not really mathematical equations because they are kind of a mathematical abstraction, you know? Yes, of course, we have probability theory, optimization theory, expectation gradient, policy function, and all of these are mathematical, rigorous, and beautiful. And they guide us here this way to represent how an AI system should be built, how its parameters should be calculated and everything. But just notice we are working here with idealized models in a simplified environment where every parameter, input, output, the meta plans, the reward systems, the reward function, the operators are all well defined. There's no problem at all. We never encounter any problems. But those perfect idealized model, they help us to understand the fundamental relationship for our learning. So you might say, hey, wait a minute, in those publications we always see pseudocode. What about the pseudocode? Can we not use the pseudocode? But yeah, but pseudocode is even simpler, you know. Have a look at this pseudocode. You have two blocks here. You compute here a low-level reward and you compute a high-level reward. And you have barely any information to code this, no? But you know what? We can compare pseudocode to the human thoughts. So let's have a look here at the low-level training. And this is the way I would explain it, no? So for a certain number of steps or epochs of your system, you just sample here a specific data point from a data set. And then let's say we use here a frozen high-level agent with a particular policy pi to generate here a meta plan. And the low-level agent, pi low, produces here a final answer called y, given here this particular set here of the task x and the meta plan m. And then we compute here a low-level reward function, or low, where we have our meta plan, our result y, and the ground truth y star. And then we simply update the policy. We update all the parameters of this policy using here the gradient of the reward. And we do this by the mathematical knowledge of policy gradient methods like reinforce PPO or reinforce plus plus or whatever you like. Having done now the low-level training of our agent, we have now to perform the higher-level training, no? And you know what? I would explain it in this simple way. For a certain number of steps or epoch, we sample here a specific data point here from here a data set. So we have here our input x and our ground truth y star. Then we have the frozen low-level agent. Pi low is used to generate here the final answer y based on the meta plan from the agent pi high. And then we simply compute here the high-level reward high, having here the meta plan, the result y, the ground truth y star, and this answers here, does the meta plan m lead here by the final answer? And then we update simply the policy and all the parameter theta h, using here the gradient of this high-level reward. So you see, in words, it's also really rather simple to explain. And we just have to calculate somehow the gradient of a high-level reward function. This is all that we have to do, more or less, no? So let's open up this video. Let's have a look at the first equation that I showed you. This is a kind of a system equation for this, no? So this kind of, let's call it, okay, a mathematical formula, serves here as theoretical models that guide here the algorithm design that we're going to develop. And therefore, this is important because we want to code this later. And there's no code without an algorithm design that we understand what's going on here. So this will allow here the researchers to derive property like Convergence guarantees stability of the complete system and expected improvement given parameter or system-wide improvements. So let's look at the first term, a policy pi with some parameters theta for the system H, and we have another parameter set here, theta, for the system low. And we have an input x and an output y. So what is this policy? This policy, as we denote in AI as pi, is indeed a probability distribution over actions that an agent can take given here a particular state or a particular input x. So in reinforcement learning, this pi AS specifies now the probability of taking an action A when the agent is in a particular and well-defined state S. And this probabilistic formulation allows the agent to explore real different actions rather than always choosing here a single fixed action, which is important for learning. And yes, you get it. Here we're kind of referencing here supervised fine-tuning. So we discover what is the difference between here reinforcement learning and supervised fine-tuning for multi-agent learning. Now, but this equation is a little bit more complicated. No, we just look here at the primary term. So what is here in the parentheses? What are we doing the summation, the integral of? So let's have a look at each component. So we have here our model or our policy pi theta high, where we have an input x and we have m. And m is now a meta syncing plan. So this goes beyond our simple chain of thought, because now we have really, if you want, an agent, a system, an LLM that is just thinking about possible solutions without implementing those solutions. The implementation is given to a second agent. This is here pi theta low. This is the low-level agent policy that we have to train, that we have to develop and then apply. And this low-level agent policy is conditioned on the same input x and the chosen plan m. So our high-level agent just creates here the, if you want here, the high-level thinking process, develops here a plan, what to do, a strategy, and then the low-level agent produces here a final answer given here with the input of x, this meta thinking plan m. And then it produces here y. So now we understand what these two policies are doing. Then we just sum here over all the m. The summation represents an expectation, the operator e, you're familiar with this in AI, over all the possible plans m. And if we have, this is for a discrete m, and if we have a continuous m, like later in quantum structures, we would replace this sum with an integral. So therefore, the parameter, of course, the parameter for the high level and low level policies are called theta high and theta low. So each agent is optimized separately, or, and this I will show you in detail, in an alternating fashion via the reinforcement learning to improve the overall performance of the system. I can give you, if you want, an intuitive interpretation of this formula. We have a high-level planning, no? This is what we call meta thinking. Thinking about our thinking. Thoughts about our thoughts. So the high-level agent looks at the prompt X. This is, for example, a task like a mathematical question or a complex task that you give to the AI, and proposes a strategy M. So if you want, it decomposes the complexity into a little more complex system or a complete strategic plan. Then we have the second agent, if you want, for the execution, and given X and the plan M. So now we have in the input X and the plan M. The low-level agent, so pi theta low, produces now the final output Y. This is a step-by-step solution or the final answer, whatever. And then, as you see, we combine those because we do have a multi-agent coordination. So combining these two probability distribution, we get a single probability distribution as a result. This is our pi theta h, theta low from X and Y over the final answers, Y reflecting here the hierarchical collaboration of meta thinking at the high level and a detailed execution at the low level. So you see, you can have a feeling for this formula, you can have a pseudocode for this formula, or you simply understand in detail here the components of this formula. So this meta thinking reasoning process, which we call M or P, this we can do for a single or multi-agent configuration. As you see, we have here two agents, a theta H and a theta L. We have here a two-agent configuration. this meta syncing here, you see here beautifully in the second term. So in the first one, the high-level agent just gives me an input X and produces here a strategic plan, a meta syncing. And then this meta syncing is together with the query X, now the input factor for the execution of pi theta low. You see, this is the content of this formula, and I think it's rather easy to understand. So the policy not only defines here the action to be taken by the agent, or in our case, a decision or output function, whatever, but does so in a way that encapsulates here our uncertainty and our variability of the probability distribution, which is indeed crucial for learning and optimal behavior in complex environments. So we do not just go with a template or we choose from 12 different templates, one specific template. No, we want to go the next step. Great. So let's come to the part where I tell you we need a spark. Please, I need definitely a spark of genius. So how we do this? This meta syncing process, this thinking about our syncing of the AI syncing for our LLMs or vision language models, they show us here they are really important because they can improve the performance of our system. So, as I showed you, this is here the simple mathematical formula from everything I told you up until now for the meta syncing reasoning process that is valid for a single, like here, or a multi-agent, like I just showed you 10 seconds before. M, from M0 to MH, is the output token of the meta syncing during solving a question, which calls the LLMs once and generates the meta syncing and following the reason auto-regressively. This is now in a stark contrast to the previous works where you had mainly construction-based methods, like sampling from predefined templates, you know, these sort templates of MRP, and then applying here supervised fine-tuning. But what we want to go a step further, no? Because this supervised fine-tuning, I will show you the performance data in 2 minutes time, those works, this fails to fully explore here the exponentially large language space that we are working in and are confined to a predefined pattern, even when using here the real efficient search algorithm like multi-modal research. So therefore, we need something else. So rather than our supervised fine-tuning on a predefined execution pipelines, the LLMs must possess the flexibility to explore freely and update rapidly given the feedback from the environment. And therefore, this is the main reason why we go here in MARL 4. This is necessary to adopt here a reinforcement learning training, but not any. This is, of course, a very specific mathematical procedure. So, easiest, simplest case to agent. One is a high-level meta syncing agent, and the other one is a low-level mathematical reasoning agent. Let's have a look at the core idea that we want to implement. Let's have some fun together and let's have a look at 4 different scenarios. The first one is the vanilla reasoning progress, where we have our standard chain of thought. This is the standard we have currently. No? We're prompting the LLM to solve a problem step by step. You know this. Then we have now a reinforcement learning methodology to optimize now the learning of the LLM and increase the LLM performance under this vanilla reasoning progress with chain of thought. We just call it VRP underscore reinforcement learning. And then we jump here to the meta syncing reasoning process, MRP. So we go from a vanilla RP reasoning process model to a meta syncing reasoning process model that we train with reinforcement learning. Using now a very particular reinforcement learning, I'm going to show you in a second to optimize the performance under this, prompting the LLM to solve the problem with a high-level task analysis and a solution plan. We're going to have a look at this. And then, of course, as I showed you at the very beginning, we use now reinforcement learning to optimize the LLM under a new schema we call MAMRP. You know, English is my third language, so I'm so sorry, I have no idea how to pronounce this, but it stands for Multi-Agent Meta Syncing Reasoning Process. And if you want, it also goes under the acronym of REMA. Beautiful. This is a new scientific study by an AI community I'm going to show you in a minute. Now, I know what you're going to say. Hey, can we not solve everything just by prompting, prompt engineering and DSPy, and TextGrad and everything? Well, let's have a look at the prompts. So a system prompt would be, for the vanilla version of the reasoning progress, you are a meta expert tasked with solving the problems step by step. This is our chain of thought formulation that, present the final answer within boxed whatever. And here's the question. So this is here the vanilla version. Then, of course, we say, great. Next one here is already our meta-thinking reasoning. So we say, hey, you are still a meta expert tasked with solving problems, but when solving a problems, your first task is, as a single agent, to provide here a high-level solution plan as an instruction for the next calculation. And then you need to follow the provided instruction that you came up with, my little AI, precisely. So now you execute your own strategic plan, showing me all the reasoning in the intermediate steps. And finally, you have all the mathematical representation done in a specific tool, use case, function calling, Python environment. And then you present me with the final answer. And then the user prompt is, here's the question. So this is here the meta thinking for a single agent reasoning progress. But now the prompt here is beautiful if you have two agents. So we have one agent, the high agent is just doing here the high level thinking, and then the low agent here, as called by the authors, is just doing here the actual mathematical reasoning work. So the system prompt for the high agent is clear. You are a math expert specialized in solving mathematical problems. You need to teach here a weaker agent with a minimal capacity in math how to solve a problem step by step. Your task is to provide a high-level solution plan for the given problem in order to guide a low-level math solving agent to solve your even complex problems. You cannot directly answer the question. You will be punished if you do include any answer in your response. You need to first think deeply and in mind and output your final instruction. And this instruction is now in the input pipeline to our low agent. And we tell the low agent, hey, my little low agent, you are a math expert tasked with solving problems step by step, following the provided instruction by your big brother. Precisely show me all your reasoning and intermediate steps, present the final answer, and just follow the instruction given by the bigger machine. Now, prompts are nice, but coding is even more beautiful. So let's have a look how we can build this. Let's go to the vanilla reasoning process, and I show you here one paper that I would recommend. And they explain here the vanilla reasoning process of our AI. So we have an autoregressive decoding process of a language model can be formalized as a series of sequential token prediction with the overall probabilities equal to the product of the probabilities of each individual step. And here we go now. Given now a language model pi theta, parameterized by multiple parameters theta, and a task prompt x, this is our input, where we have from x0 to xn, n tokens in our input. The vanilla reasoning process directly generates here response y, where we have from y0 to yl, l tokens. And the probability of generating y is now exactly this one here. So our p theta, given the input x, given here the result y, is here this product. So we have here our x0 to xn and our y0 to yi minus 1, where I runs from 0 to L. So in this specific case, where the response contains structured intermediate reasoning steps, the process is also what we call a chain of thought. This is what we do here for the vanilla reasoning process. Great. But then, you remember, we have to train this system, no? I mean, yeah, you can go off the shelf from Hugging Wave, you just pick a model, but hey, let's build this model, no? And our data and our domain knowledge and so on. Maybe we want to understand how to improve it. So training now our vanilla reasoning models with supervised learning and reinforcement learning. So with DeepSeek, the hype, beautiful. The decoding strategy here follows here the vanilla reasoning process. This is the easiest one. Can be formulated as a deterministic token level Markov decision process. And the optimization problem, because everything in the AI is more or less an optimization problem. So we have now a loss function that we want to optimize here. And this loss function L can now be noted depending on the parameters theta as this one. I hope you are familiar with this. Never mind. R is here the reward function, presents the reward function comparing the generated answer Y with the golden answer Y star, the ground truth, also called, for any question X sampled here from the dataset D. So this explains exactly this term here. And now, if you want really to compute this with a mathematical algorithm, if you code this, now to compute the gradient of the loss function of this particular loss function with respect to the policy pi theta, we know we have a good old friend, the reinforce algorithm here from 1992. Can you imagine this? And it applies here the log derivative trick, which I'm going to show you in a minute, and then it computes the gradient as follows. So we do have here the gradient of the loss function that we need to solve here this optimization problem for this particular loss function, given that we have a look at this as a Markov decision process. Beautiful. Now you know that there are some ideas how to have a mathematical optimization or simplification. And you know PPO, no? Since strict online sampling and the gradient calculation can be really computationally expensive, the PPO, the proximal policy optimization, remember OpenAI 2017, was widely adopted for its high training stability and the sampling efficiency. See, we go for the stability of the system. And you know from OpenAI, the PPO loss function is defined in this particular way as a kind of an approximation, where we have a ratio between the current and the old policy, and we have the advantage of the policy, the extra reward over the average reward. Yes, there is some link to GRPO. And then in 2025, Reinforce++ was published, and this is a real nice mathematical trick, if you want, an optimization. Combines the simplicity of the reinforce algorithm with the enhanced training stability of PPO. So we build upon the classical reinforce framework. It further improves the performance by incorporating those clipping techniques or technologies from PPO, gradient clipping, mini-batch update, and advantage estimation. If you were not familiar with this, never mind. Here is the classical reinforce algorithm if you just want to fresh up your memory. And here we have the reinforce++ enhancement. Of course, we have a token level, callback blah penalty. We have the PPO clip integration and the batches. If you want to see the complete paper, this is from beginning of January 2025. Here, Reinforce++, a simple and efficient approach for aligning LLMs. Great. Yes, you even have it available here in a GitHub. So they say, hey, great. So we know PPO, we know the direct preference optimization DPO, we know here different Remax here, whatever. And from DeepSeek R1, we have now the group relative policy optimization GRPO. They say, you know what? Knowing all of this, we build now our Reinforce++, and this system now exhibits superior stability, even compared to GRPO from DeepSeek, and it even achieves a greater computational efficiency than OpenAI PPO, while maintaining a comparable performance. So this is a real deep dive mathematical optimization, how to code this given certain limitations of the system, but we have a solution how to compute this. Let's end it at this level. Beautiful. Let's zoom out again. So what we have, let's say we have a mathematical question like this one. Hey, this is our equation, identify everything for particular values. And then what we have more or less three ideas. No? We have here, if you want, the supervised fine-tuning LLMs. No, we have rejection sampling, and we're just searching among the different meta thinking templates and the reasoning templates and whatever you have here, whatever is a predefined knowledge flow structure for some reasoning, for some mathematical solver. We can have this as you want here as any kind of template. And then we have a question, we have a pre-trained LLM, we use this, we have rejection sampling, we see what works, what is the best solution, we have a supervised fine-tuning, and our LLM gets better in the training phase. You see this if you look here at the output. Exactly, you have our classical chain of sort, and you verify this. So whatever you know from the classical reasoning topics, no? Then we have with DeepSeek R1, there was really some disturbance here, yeah, in the force. because we have a question, we have now a powerful LLM, we do have the complete reasoning, we calculate here in RL here the outcome rewards, okay? And then we have here in the training, in the classical reinforcement learning, the GRPO, the group relative policy optimization, we just train our LLM to get better here with a particular training data set. If we look here at the output stream, you see classical R1. Given that, wait, hold, let me double check my steps. So wait, I'm confident, so the final answer can be. So we do have here this reasoning, and I've shown you that currently, especially in my videos about Carnegie Mellon University, they try to further simplify here GRPO to LCPO, and they build the L1 model. So if you want here in the theoretical development of this optimization of GRPO, this is the video for you. But today, as I told you, we want to understand here and build something from a pure mathematical point of view. So let's have a look. We are here again at reinforced meta-thinking agents. And as you see, we have here our two agents now suddenly. We have the high-level agent that is only doing the strategic thinking. And then we have the low-level agent that is just doing the mathematical reasoning and the execution in your, let's say, Python or C++ environment. Great. Break down the problem, understand the question, verify the solution, the meta-thinking, the reasoning steps with the meta-thinking instructions. And you have here the steps and the thinking process from our two agents. So this, let's call it REMA, separates here the meta-thinking and the operational reasoning steps here in a multi-agent system. So if we know now the mathematical implementation of this new advanced reasoning process here for two different agents, the next question is simple, no? How we train this dual agent system, this multi-agent reinforcement learning system. What algorithm do we use? Now, as I told you, let's just look here at the right-hand side. It is rather easy. No? We have two systems, so guess what? The easiest solution, at the one point, we just freeze here one agent and the other agent is now trainable. And then we do exactly the opposite. We have here the high-level agent that is now freed, is now trainable, but of course only with a low-level agent now frozen. So therefore, you have an alternative learning step. This is an iterative process that goes on. And you integrate here the learning from the low-level agent and here optimize at the same time the high-level agent in the strategic planning. Couldn't be simpler. No, you just jump. And in the end, you received here a system optimization by multi-agent reinforcement learning. Yeah, if you want to see the prompt for the metacognition reasoning to rewrite the prompt, it is so simple. I'll just show you this. Metacognition reasoning to decompose here the complex mathematical problem and the prompt for generating a final answer using here the question and the metacognition reasoning here from the high-level agent. Couldn't be easier, no? And now we are at the definite facts here. So this is the paper. This is here by Jiao, Tong University, University of British Columbia, University College London, and Shanghai Artificial Intelligence Laboratory, March 12, 2025. REMA, learning to meta-think for LLMs with multi-agent reinforcement learning. So REMA, here I have it. Reinforcement meta-thinking agent REMA. Beautiful. You know, I have an own list of just abbreviation because I just forget what it means. I have more than 250 abbreviations from the different teams here around the world. So yeah, that's fun. What is REMA? What is important for us to remember? A null framework that leverages here the multi-agent reinforcement learning, our typical MARL, to explicitly do this meta-thinking, encouraging LLMs to think about thinking. This is not so new because we had in, let's say, a swarm of AI agents, you know, we had an executor, we had one instructor, we had one that was thinking, we had one verifier. So this complete idea is not new, but there's an interesting mathematical implementation. So let's have a look at this in more detail. And maybe you find something new or surprising you haven't seen before. So let's look at a high-level agent, and you know we have here to optimize here the gradient. So if you look at this formula, and this is now the second system formula we look at, you might say, okay, so what do I see here? What does it mean here, for example? Yeah? If you have an expression like here, this E functor, it means simply that during the training you calculated some expression here, like a reward or gradient component for every pair in the data set, and just take the average of the values. So this average given here an estimate E of the expected value of that expression under a specific data distribution. Rather easy. Other terms like this term, I will explain this in a moment what it is. We have a calculation methodology. It's called a Monte Carlo methodology. But let's go here to this term now. What does this term mean? So in our probability notation for AI system, this tilde operator means more or less is sampled from. So when we write now this particular expression, and M is now our meta plan, this detailed strategic plan what to do by our high-level thinking methodology, you see this meta plan is sampled from our policy pi theta high, so our high agent, where given the input X, so my mathematical task, and it produces here the meta thinking plan M in all its different steps. So this indicates here that the meta plan M is drawn from or is sampled from, this is the tilde operator, from a probability distribution, this is our pi, defined by the high-level policy pi theta h. It doesn't mean that it contains or is part of, it is just remember, or we are working with probability distribution. Careful not to get this wrong. So, okay, we have to start from the beginning now. Okay, so high-level agent gradient. We have to calculate this. This is how the system works. This is the code we want to write. So, let's start at the first. Yeah, let's make it systematic. So, we have here a nabla J. This is here the gradient with respect to the high-level agent's parameter theta h of the overall objective J. And the objective measures now the expected performance or the reward over all the data and all the agent decisions. Do you know this? J is this objective function. So it quantifies how well the agents are performing overall. And especially in reinforcement learning, it is common to define this particular goal as maximizing the expected reward. This is our optimization problem. So J here encapsulates here, if you want, a performance metric for the complete system. The gradient of J that we are looking here now with respect to the parameters of the system, so theta h for the high-level agent and theta low for the low-level agent, tells us now how to adjust these parameters to increase the expected reward, thereby leading to a better decision-making and output generalization of the system. You remember this in backpropagation here from the simplest neural network? With a gradient, we know in what direction to go next. So this gives us here the gradient of J indicates the direction to our solution, where to go next, which steps to take here in what particular direction on a particular hyperplane, on a particular loss function. Avoiding here local minimum, maximum, and everything. Great. Now J, if you code it, has here a particular form. So let's have a little bit a deep dive on J. J is defined as the expected reward that the system, or the joint multi-agent system, receives when it generates an output Y. So for example, a typical formulation of J for two agent is this term. So what we know X stands here for the input, or that's the input state. Y star is here the correct or the ground truth or the desired output, whatever you like to call it. D, so the pair X, Y star, is sampled from the dataset D. D is our training dataset. Y is the output generated by the specific agent. This is not the ground truth. We want to have here the minimization from Y to Y star. Then R is our reward function. It is here, if you want, depending on the parameter, on the output Y and our ground truth Y star. The reward function evaluates the quality of the output Y. And then we have our policies, the joint policy of the high level and the low level agents. And you see, great, but what does this mean? What is the mathematical operation of this? Is this a functor? What is this? So Here we have the inner expectation. The inner expectation is equivalent of taking here a weighted or normalized sum of the reward function over all possible outputs y, where each output is weighted by its probability of being chosen according to the policy of the system. So this is rather easy to understand, this particular notation. So let's have a look. This probability distribution, if you want to understand it on the next deeper level. Yes, I know it hurts, but never mind. So we have our policy pi theta high and pi theta low. Input x, output y defines a probability distribution over the possible outputs y for a given input x. So this means here, this summation sums up to 1, where y here, the capital Y is here the set of all possible outputs. So then what we do, we have a weighted average or a normalized summation. So the expectation operator E that we have here calculates now simply the average value of a function, in this case it's the reward function, over a probability distribution. So for a discrete distribution, the expectation is therefore simply this sum of y over all capital Y, element of all capital Y's here, of exactly here our pi theta high, theta low, input x, output y of the reward. So this sum, if you want, normalized now in a sense that the probabilities all add up to 1, ensuring that the result is a weighted average of the rewards. And this is exactly what we wanted for, if you want, the inner expectation. Is there an intuition I can explain this to you? Well, I try. So for each possible output y, the reward given now of this particular output y in reference to the ground truth y star is now simply multiplied by the probability pi that the output is produced. And these products are then summed over all outputs, giving here the average reward you can expect when following this particular policy. Maybe this helps you to understand it. Now, the other term is the outer expectation. What it is, it takes you the average of the inner quantity, which itself is an expected reward of a given input x, over all the input-output pairs in the dataset. So this is here, this particular notation here, over all the different datasets, different pairs in the dataset D, we have now the outer expectation. So it sums here the inner expected rewards for each pair and divides by the total number of samples. And effectively what it does, it's normalizing the sum. So what this step does, it aggregates here the performance across the entire dataset. And this is what you want, because therefore you ensure that the training objective J represents the model average behavior on all the example rather than just on a single instance. Great. So we have now hopefully an idea what J of our two-agent system means and why we have to calculate here the gradient of J. Now, if we calculate the gradient of J, we saw that this is a system equation. So let's have a look here at the first term. You're not gonna believe it. E is still our expectation operator. So we first take an expectation over the pair drawn from the training data set. And X is still our input and Y is still our ground truth. Great. And third point, the summation M is sampled from here, the policy pi theta high. And you know, pi theta high has here exactly, it generates here our plan. So this is the high-level agent's policy, which assigns probability to different plans M given a particular input X. Okay, next term. Okay, next term. This term is a little bit challenging, but never mind. This is just the derivative of the high-level agent policy with respect to its parameters. So you see pi theta high. It appears here in a standard reinforced style gradient term, indicating how adjusting here the parameters theta high changes here the probability of selecting a specific plan M. And then comes here our final term. And now you know this final term because we just had a look at it a minute ago. So inside the parentheses, we compute here the expected reward over the final outputs Y, drawn from the low-level agent policy pi theta low, given an input x, given here a strategic master plan M, and the output y. And of course, R is our reward function, the reward measuring how good the final output y is compared to the golden, to the ground truth y star. So I hope this helped you here, or maybe you said, hey, that's so easy, I never thought it would be that easy. Well, of course, yes, if you have then to calculate this, there are some programs, there's a log trick here. If you want to compute a gradient of an expected reward, it depends here on a stochastic policy. Directly differentiating through the probability distribution can be challenging. This is a very friendly formulation. And instead, there is this, what they call a log trick. And if you apply this, you find this is a much easier to calculate structure. So how this trick now works in the policy gradient, so you consider here an objective function that is the expected reward that we just have a look at, and the direct differentiation with respect to the parameter theta gives us this, and by applying this particular trick, you see we can rewrite now the gradient of j in this particular formula, and this makes life so much easier if we code this and calculate this. So you see, easy. We looked at a complete paper just by looking here at its main mathematical formulas that define the system behavior. And it is a rather complex two-agent system behavior. But I hope you saw mathematics can be nice. Now, let's come to the paper, because if we implement everything, if we code everything, and if we run everything, if we build the models, we see that those models have a particular performance. Now, let's go the next level. Let's see what is the result of all of this. So we have here for different benchmark, we have here an easy benchmark, a medium benchmark, and let's call it a hard level benchmark. And now we have here three versions. Yeah? We have here, if you want here, the reinforcement for the base model. Then we have here what we just talked about here, the reinforcement learning under the meta thinking design. And then we have a reinforcement learning from the supervised fine-tuning model. So now it's easy. You see here a particular performance. Easy, we have reinforcement learning from supervised fine-tuning. This gives us the best performance, 92% plus. If we go to the medium, you see it is still reinforcement learning from supervised fine-tuning, has simply the best performance. But things change. And this is something I do not understand. And we're going to talk about this in a second. Because suddenly our orange here, reinforcement learning from supervised fine-tuning, has a problem. And now they argue our new methodology, the reinforcement learning under the meta thinking, becomes now the best model. Now have a look at this. We kind of have here a linear performance increase, and then we plateau out or even fall back a little bit. Now this is different. So let's have a look what this really means. Yeah, the text is here, reinforcement learning here in orange from supervised fine-tuning achieves superior performance, but it struggles to generalize to more challenging problems, the hard problems, you see. And in contrast to from base, so under meta thinking demonstrate the ability to solve previously unseen harder problems, with the latter further enhancing the performance if you go to real hard to solve problems. However, if we have a closer look at our reinforcement learning from supervised fine-tuning, there's a particular thing that they have done. Yeah? So they collected a small amount of chain of thought traces, reasoning data from GPT-4 Omni. Now, from today, mid of March 2025, I have to tell you, the reasoning traces, the mathematical reasoning traces of 4 Omni might not be the best mathematical model up to date. So therefore, okay, so you take here some chain of thought reasoning traces, and with those that might not be the best, you fine-tune now your base model with supervised fine-tuning, the classical SFT methodology. And then you train this tuned model on mathematic with a binary outcome reward. Now I understand that if GPT-4 Omni was good at producing here chain of thought traces in the easiest case, in the medium case, but now the training data generated the synthetic training data by GPT-4 Omni might have not been up to the job. Maybe GPT-4 Omni itself could not generate here the chain of thought reasoning traces. And therefore, if you then fine-tune the base model on this data, the performance for the real hard problems are not there because the training data do not have the quality necessary for a performance increase. So this means if you only see this image here and you think, this is an indication that this system is not working, I think this is the wrong conclusion. Because if you have a deep dive and you understand, hey, this is just, it was trained in a supervised fine-tuning methodology with another model synthetic generated chain of thought reasoning traces, maybe those reasoning traces were not up to the task. It is not that you can say the methodology failed, because we have indication that in easy and medium it did work. Okay, now let's do the same here and let's have a look here at the best performer, at the latest, at the new topic, at the main paper that we had a look today, reinforcement learning under this meta thinking. So they start again, collect a small amount of high-level meta thinking data, again from GPT-4 Omni. And then they fine-tune a QN 2.5 Mat 7B instruct to increase its meta thinking abilities. This is here the junior, this is here the senior, and this is here the junior. And make sure that it acts as a high-level planner only. So this is now interesting. And then we do the reinforcement learning alignment also of a QN 2.7 Mat 7B model as now the low-level agent in collaboration with the high-level instruction with a binary outcome reward. So this is now interesting because suddenly we have two different models that are here the 7B instruct and here only the 7B, and they are also, although here they are trained on GPT-4 Omnis, there's now kind of a compensation through the reinforcement learning as a low-level agent. So, this is an interesting choice how to implement this and get this performance, and I have immediately 5 other ideas how to do this, but maybe you understand what I want to indicate here. Yeah, let's come here at the official benchmark as published by the authors, and here to tell you, okay, we have here the model Llama, and this is a QN 2.57B instruct, this is an 8B instruct, and for all the different benchmarks, and as I told you, we have 4 different scenarios. So this is the vanilla, the chain of thought. This here is the vanilla, then if you want trained here with reinforcement learning. This here is our meta thinking version, and this here is the paper that we just had a look at. So let's have a look at this. We are here at LLM as a judge benchmark. This is a very specific kind of a benchmark, LLM as a judge, and you see here this, or the performance data, you see in some areas here, for example, here for a Llama model, it really works out. But as you see for a QN model, no, it doesn't work out because the others are better. So we have here a model-specific performance, allows us to have some ideas why a Llama might be sensitive to this improvement and why with QN you don't get any improvement at all compared to the other models. But also they give us here this performance data, and this is now on mathematic benchmarks. So this is now really interesting. We have a Llama 3 and a QN 2.57B instruct, and here you kind of see an interesting thing. At first, it is not really always the best model. It's not really always outperforming here. But let's have a look here at the last line at the average line. If we calculate everything from this 1, 2, 3, 4 different scenarios, you see here we have on average over everything here a performance, let's say from 50. Here we have also a performance of 50. Here we have also a performance of 50, maybe 51. And then after doing all of these things, having 2 agents, train 2 agents iteratively, have here this extreme amount of training and optimization, and what we achieve at the end, we go with from, let's say, 51 to 53. So this opens up now the question, how significant is this performance improvement of a multi-agent, meta-thinking, reasoning AI done via this new reinforcement learning methodology, REMA. Is this really a systematic methodology improvement that suffers here from an implementation because some of the LLMs did not provide here an optimal chain of thought reasoning trace? Or is it that the methodology itself needs to improve further? Just want to show you this limitation by the authors themselves. And they say, additional, our formulations are currently limited to single turn interactions. And they say in the future, we aim to refine these methodologies and extend them to a multi-turn. So I think if you have two agents and you only allow a single turn interaction, this might be a real limitation. And I think with the next step to multi-turn settings, this would indicate here the path forward to our future to evaluate, hey, is this methodology the best one and how significant are the improvements? So there we are. I hope you enjoyed it. I wanted to show you this mathematical formulation that you find in the research paper. They are extremely helpful. They are kind of an abstract logic representation of the main ideas. And it is those mathematical formulas, if you code this system that you are then implementing in C++, in Python, whatever you like, without an understanding of this, what are you summing over? What is your integral? What are your boundary conditions? How is this system interacting? What is, if you want, the flow here of the optimization? What parameters are you optimizing with what particular trick? What are the gradient calculations here for your J? If you don't know this, you have a hard time understanding new models. But if you're familiar with this, you understand these are just tools that help you to further understand the system. They enable you a deep dive into the algorithm, into the inner workings of our AI models. And I hope I've given you here today a little bit of an impulse that you say, hey, this looks great. Why not explore more of this?